Yeah. So yeah, over here. So D'Alembert's formula, if you have initial conditions, way, then how do you find the solution? The solution is basically, so you have so you divide the initial shape into two parts, one that is going forward and one that is going backward, right? And then what happens to the initial velocity? So the initial velocity, you sort of integrate uh, from x minus c naught to t to x plus c naught to t. So what you're doing is when t is equal to 0, then you're integrating from x to x, right? When t is not 0, you're integrating from some value to the left of x to some value to the right of x. In a sense, what that means is that your velocity, the effect of velocity spreads over time as well. So your velocity, and yeah, you integrate it. So this is D'Alembert's equation. Let's take an example. So you have pi of x comma 0. That means the initial shape u of x is, let's say it is 1, uh, when from minus a to a, and is 0 whenever you have modulus of x greater than a. And let's take initial velocity to be 0, right? For the simple case. So v of x, right? Now, let's say we have to draw the solution. Um, how do we draw the solution at t is equal to 0? Well, at t is equal to 0, it's already described quite well. So at t is equal to 0, right? Cool. So a is minus a, and this has to be 1. So this t is equal to 0. Fair and simple. Right? So let's consider t is equal to a by 2 c naught. If you substitute that in D'Alembert's equation, you see that since initial velocity is 0, you just have to worry about this part, right? So then when you substitute it and you break the initial shape into two forms, one that let's say goes to the left, one that goes to the right, then you have u of x minus c naught t, and t is equal to a by 2 c naught, so that becomes a by 2 plus u x plus a by 2. Right, so if you draw this, what you see is right, so there are two ways now. Um, one that goes originally, like I think we had, we divide this into two parts, superimposition. So one, let's say, goes to the right and one goes to the left, and it has moved by uh, a by 2. So one goes here, the other goes here, and here you'll see, let's say, right? So now if we superimpose one over the other, you'll see some shape like this. So overall, it's a shape like this. Yeah. So, and now similarly, let's say if we take double the time, t is equal to a by c naught. So then each has traveled by a. Then what we observe is it's leading to make the same height. Yeah. Assume that these two are of same height. Um, yeah. So this will move, right? So this part is moving here. This part is moving here. So but this is the overall shape. Awesome. So now let's say if you want to capture this behavior, I can keep going. Let's say what is E is equal to 2a by c naught. Like what is the profile? I can keep going. But you want to capture. You don't want to draw. You want this each time. Then how do you capture it? There's something called an XT diagram. What are XT diagrams? Simple X on one axis, right? So you have your X on one axis, not your X, but the coordinate X. And this is the time coordinate. Right, so of course we are earlier we had amplitude in the y coordinate. Now we don't have amplitude. So there's some loss of information, but the maybe you can use colors, maybe you use intensity, something to show um, the amplitudes. So yeah, let's just see the expanse of it. So originally it was from -a to a, and we know that you can divide it into two parts. One was going forward, one was going backward. So the forward going wave, of course, like you go forward. Just assume that it's interacting, intersecting. Right? Yeah. So what is this slope? This slope is sort of t by x, and we know x by t has to be c naught, the wave speed. So this particular slope, it will be 1 by c naught, because it is t by tx. So this is the slope. Yeah. So this is the xt diagram, and the Dalton equation. If we know the initial conditions, the if we know the initial uh, the shape of displacements, and if we know the shape of velocities, then we know we have this equation. We can integrate it, and then we can get something like next to diagram. We can know how it's spreading. Yeah. So that is my first lecture. Uh, I hope it gave you some insights into uh, through it. Like yeah. So we introduced wave propagation in architected materials. Um, what are metamaterials? What is meta? Meta is something beyond. So materials which are behaving more than what they are made of, and it's because of the intricate designs, the internal architecture that we're because of which they are behaving like that. And we will talk of some effective properties that we can get. And some of those are static. Let's say pentamode talks about how bulk modulus can be greater than zero, but shear modulus can be zero in a metamaterial. So it's a solid that behaves like a liquid, sort of. And then you have auxetic, where Poisson's ratios are like negative, so negative Poisson's ratios. These are sort of the effective, new properties. And in dynamics also we covered some of that, and we spoke about negative modulus, negative density, and what are the ingredients, like broadly either you can use periodicity, or you can use locally resonant inclusions, and we spoke of how these principles are common across various fields because the wave mechanics is sort of similar, the equations are similar. Then just a brief introduction into the phenomena of waves, like what are waves? We say that it's a disturbance that is transmitted through space, whereas the medium itself is not transmitted. And some important terms like dispersion, right? Dispersion. So we have two waves of different frequencies, let's say F1, F2. So both tend to travel at different velocities C1 and C2. And if you have a broader, like something made up of multiple frequencies, then you'll see that various frequency components travel at different wave speeds, and that changes the shape. And in dispersion, the energy is conserved. It's just the speed that is altered. So we use this principle fundamentally in metamaterials, and then we speak of dissipation. Dissipation specifically talks about loss of energy um, with space-time, and there has to be loss of energy as the wave is propagated. And then we talk of distortion. Distortion typically is a nonlinear phenomena where you have some shape and then that shape distorts. We speak about the example of surfer riding a wave and the wave collapsing, and then we speak about attenuation. Attenuation, like power transmitted in attenuation is zero. So it's not really, it's actually lack of propagation. So in a way, you can say attenuation is not a wave. It's a wave phenomenon, but it's not really propagation, right? Then we just like take the example of a string, and then we try to derive the wave equation for the string. Then we highlight what are the assumptions in this. Then simply using Newton's second law, we write the equation. Say with this tension T here. Uh, let me use a pointer. Can I use a pointer? Yeah. So this tension T on both ends of the string, and there's a body force Q, and there are some angles. It's small angles. So we make some assumptions like the length, overall length, is approximately equal to the x coordinate. Then we say because it's that the vertical deflections are not high, so angles are small, so sine theta is approximately equal to theta. Yeah, we see that, and then we say that if theta further, like we can break it into dou y by dou x as the slope. Since tan theta is approximately theta, so tan theta is dou y by dou x. So So yeah, in a way we are writing sin theta as tan theta and then tan theta is divided by dou x. That's just some assumptions that make our life easier. Then then we take this term C naught, which is square root of T by rho. T is tension, rho is your linear density, uh, in a sense like yeah, mass per unit length. And then we derive the standard wave equation. We see that it is a double derivative with respect to x is equal to some constant and double derivative with respect to t. So there's a space derivative and there's a time derivative, and that is fundamental in a wave equation. How do you solve this? Like, so you have to, essentially, you have to realize that it is um, even you can break down something into forward and backward waves. So this is a forward wave and this is a backward wave, and the forward wave is a form of x minus c naught t, and the backward wave is a form of x plus t naught t. Then we D'Alembert's formula, and so if you know the initial shape of displacements and if you know the initial shape of velocities, then how does time evolution take place? Um, so that's a really useful formula. I think the mathematics of how this formula was derived has not been gone into in this particular lecture, but it would be uh, worth looking at. Then there's the velocity part. So here we take an example where velocity part is zero, just to see what happens to the initial displacement according to this equation. So we have an initial displacement, and then we see that it is broken into two parts. One that is going to the right, one that is going to the left, and this is how the shape looks. And yeah, similarly, you see a time evolution of it that can be plotted in an XT diagram where this is the extent of the wave, and this is going to the right, and this is going to the left. Yeah, so later we'll have a look at another system. So this system, like what is important to note is we assume a particular wave speed c naught. Um, so this is a non-dispersive example. So we'll have a look at some system later, which is a dispersive case. So then I think a lot more clarity will come. So thank you for joining. Thank you for listening.